Actually, before I do that, I'm going to give you a little bit on preheat versus post-heat. So preheat, there's 3 levels of preheat. Does anybody remember what level Mike Baumforth said yesterday for Martin-Siddick stainless steels? What temperature he said you had to preheat the steel to? It's like 600 degrees Fahrenheit, okay? How'd you like to weld on a piece of steel that's at 600 degrees Fahrenheit? Okay, it's not very comfortable. And when they had the problem with the Seawolf submarine, these guys had to go into enclosed containers where the steel had to be at 400 degrees Fahrenheit to prevent the hydrogen cracking. They had to wear blue jelly suits. They were only allowed to be in there for like 20 minutes at a time. So they'd have a little cart, like a mechanic's creeper, to go underneath a car. And they'd roll them in there, and they'd have to have someone outside because this was a confined space. And they put them in blue, they called them blue jelly suits. They had to wear this suit that had this blue liquid in it that would cool them down because they were going into a 400-degree oven to do their welding. And they had respirators so they could breathe cooler air so they wouldn't burn up their lungs, okay? But they go in for, like 20 minutes, and then they have to come out and have a rest, and another guy would go in there. It got a little expensive to build that submarine, okay? But it's because they had too high a strength and didn't have good enough hydrogen control. So there's 3 levels of preheat. One is 50 degree, must be greater than 50 degrees Fahrenheit. One is you heat the steel from, let's say, 100 degrees Fahrenheit to 300 degrees Fahrenheit. And the third level is greater than 300 degrees Fahrenheit. Well, what are we doing with each one of these? The ASME boiler and pressure vessel code says you shall not weld on steel if it's below 50 degrees Fahrenheit. I don't care if it's the mildest steel in the world, you don't weld if it's less than 50 degrees Fahrenheit. The structural welding code, which is probably this, well, these 2 codes, ASME boiler and pressure vessel code. ASME is American Society of Mechanical Engineers for all you MEs. And the boiler and pressure and the structural welding code, which is basically the welding engineers or welding society, but civil engineers use it. Anybody building bridges and buildings uses this. Anybody building pressure vessels uses the ASME code. This says basically for less than 1/8 of an inch, you've got to be at 32 degrees Fahrenheit or 0 degrees centigrade. That's if you're 1/8 to 3/4 inch inclusive. Otherwise, for different steels, it might be 50 degrees or 100 degrees. Here's a steel over here, and it's going to be 32 or 50, depending on the thickness, okay? Why? They got a minimum temperature. Well, obviously, you don't want to weld on top of ice, right? Why does ASME say 50? Because even though you can't see it, there's a layer of moisture on steel. There's a layer of moisture on that table, as we're talking right now at room temperature. But as you get lower and lower in temperature, towards the freezing point of water, that layer of moisture gets thicker and thicker and thicker. 50 degrees drives off enough moisture that they have found they don't get cracking by welding on steel that's above 50 degrees. So that you've got to be a 50-degree minimum surface moisture. You got to drive off surface moisture, no matter how mild the steel is, no matter how low the carbon is, no matter how low the hardenability of the steel is. You still got to get rid of that surface moisture, and that's why the 2 codes say 32 degrees, 50 degrees, whatever. You don't weld on snow, under snow. Okay, 100 to 300 degrees F. What am I doing? I'm slowing the cooling rate. If I look at a thermal profile for striking an arc, temperature versus time, very rapid rise in temperature up to the melting point, and then it cools down on an error function solution for all you mathematicians out there, which is all of you MIT students. but it slows down to some ambient temperature. If I'm heating up rapidly to, let's say, 2,500 degrees Fahrenheit, 1,200 degrees or 1,300 degrees centigrade, or actually it's about 1,600 degrees centigrade, and I cool down to room temperature, this stuff gets to low temperatures within a couple of minutes, and I trap all that hydrogen. Remember, 25 degrees is the worst temperature I can be at. If I heat it up to 100 degrees or 200 degrees, it will cool down, but it will cool down to a higher temperature, and it will stay at that temperature for this great big piece of steel that weighs several tons for an hour or two. And that allows the hydrogen to diffuse out. I'm taking care of that. I'm taking advantage of that little V-shaped curve I showed you. At higher temperatures, even in this temperature range, I'm going to not have minutes before I get down to room temperature. I'll have hours before I get all the way down. And it's like doing a bake-out at either 100 degrees or 200 degrees or 300 degrees, whatever my temperature was that I preheated to, right? Above 300 degrees, I'm tempering the steel. And by tempering the steel, turns out steels will lose their hardness. If you form martensite in the welding process, and you then hold it at temperature for an hour or whatever, once you get to 300 degrees centigrade or 600 degrees centigrade, anyway, 600 Fahrenheit, you will actually 300, you start to see a drop off in hardness. And so if this is 300 Fahrenheit, you actually will have enough time, this is probably log time as I've drawn this, you'll have enough time in here above what you would have if you were just letting it cool to room temperature, it just cooling down and being quenched to room temperature by the steel. So what am I doing if I start looking at my Venn diagram? Okay, the first one, I've got whatever stress I've got some hardness, which is fairly large, but I'm trying to make the amount of hydrogen circle smaller. So my Venn diagram, I'm reducing the hydrogen by getting rid of the moisture. On this one, I'm doing the same thing, but I'm reducing the hydrogen by giving more time for the hydrogen to diffuse away, because this steel is even harder. What am I doing here? I've got my Venn diagram. I'm trying to reduce the hardness and the hydrogen. I'm working on both of them, okay? So you won't find this explanation anywhere. I made it up a couple weeks ago. No, I did. As I was looking at preheat and said, well, and I've always sort of known it, but until I had to teach it to you, I hadn't really articulated it. But if you think about a Venn diagram, they just talk about preheat and they say, this is the preheat you use. It's a cookbook. You go to Stout and Doty, it tells you. But if you actually want to start thinking about it and how we control hydrogen, we walk through it this way, okay? So that's enough for today. Tomorrow we'll be here and hopefully we'll finish up preheat and post-heat and all that stuff.